Okay, in this lesson we're going to study how to convert an equation with rectangular variables into an equation with a polar variable, vice versa, how to convert an equation with a polar variable into an equation with a rectangular variable. Okay, so I just want to basically say this up front, that whatever we get for an answer in this section is actually the same exact thing we started with, just written in a different format. Okay, so we're trying to get rid of the old variables x and y and replace them with variables r and theta, or vice versa. Starting with equations that have r's and thetas in them, try to eliminate them and make equations with x's and y's. Okay, many of these are familiar shapes too, not all of them, but some of them, most of them. So let's just get started on this first one. So for the first one, we would literally replace y with r sine theta and replace x with r cos theta. Okay, so that's just going to basically give me r sine theta equals r cos theta. Okay, you can bring everything to one side and factor out an r. So if I subtract the r cos theta from both sides and factor out the r, I get this statement. And this tells me that r is 0, or sine theta minus cos theta is 0. In other words, sine theta equals cos theta. So I'm just using that zero product property. I know that this product is 0, and I've taken each root of it. So I've got r equals 0 and sine theta minus cosine theta equals 0. Okay, this first statement is not very enlightening. If I had to plot that, it would basically represent a circle with radius 0. In other words, it is a graph simply of the origin. Or we actually call it the pole when we're using polar graph paper. Okay? The second one is a little more interesting, especially if you divide both sides by sine theta, or by cos theta. So if you divide both sides by cos theta, you learn that tan theta is 1. In other words, the angle that probably should come to your mind first is inverse tan 1, which would be pi over 4. So there are actually other solutions to this, like 5 pi over 4, etc. But just bear with me here as we kind of plot this out and add it to the graph of the pole that we did earlier. So r equals 0 was that pole. Theta equals pi over 4 is anything that has an angle of pi over 4. So it could be any of the blue dots that I just added to my graph. If I decide to make r positive, that would be this entire ray extending into quadrant 1. If I allowed the r to be negative, that would be this entire ray here into quadrant 3. In other words, I've just recovered the graph of the line y equals x. So look back at the original question. Remember I told you that this answer would be no different from the question. It's just a polar version of it. Okay, so the answer to this question is 0 equals pi over 4. Now I don't really need to allow or use the r equals 0 answer, because when I see something like theta equals pi over 4, I give myself the chance to choose any r I wish, including r equals 0. And if somebody told me, hey, graph pi over 4, here's what I would do. I would start with supposing that the r was 0, and then go out to r equals 1, and then go out to r equals 2, and r equals negative 1 and negative 2. And I would have plotted that pole point anyway. So theta equals pi over 4 is the answer. Now this next one, there's a little typo here. This should have said y equals x squared. And so let's take a look at that one. On this problem, we would go ahead and do the same thing. This time we're going to have r sine theta equals, and now it says r cosine theta quantity squared. So let me erase this problem here. The right side is going to be a little more complicated. It's going to be r cos theta quantity squared. In other words, r squared cos squared. I still plan on doing the same thing, bringing everything to one side. So we'll do 0 equals, and we have r squared cos squared theta minus r cos theta, r sine theta, like that. And we could pull out an r. So let me take my work up here. 0 equals r times r cos minus sine. Should be a squared on that. And this gives me two solutions. Again, r is 0, or r cos squared minus sine is 0. The first one gives me that trivial graph of the point at the pole. The second one gives me r equals sine theta over cos squared theta. which can be written other ways. For example, you could write it as tangent times secant or something, but the point is, if you give me any theta now, let's say pi over 12, pi over 8, pi over 4, pi over 6, I'll just plug it into this, get an r, and plot that point along the angle you gave me and at the distance that comes out of it. Does anyone know what this graph is going to end up looking like? That's right, y equals x squared. As promised, nothing will change graphically. So the answer to this problem is r equals sine theta over cos squared theta. Again, I don't need the r equals 0 case because that actually would happen anyway if theta was 0. See, if theta was 0, I would get r equals 0 anyway. So that point would just get double plotted. Let's take a look at the next one. Let me erase my work from this previous one, just leaving only the answers for the previous problem. This next one would give me 4 times r cos theta times r sine theta. That is literally x and y. And this gives me 4r squared cos theta sine theta equals 9. And bringing my work up here, I can divide by 4 cos sine theta. So I get r squared equals 9 over 4 cos theta sine theta. And it's actually kind of a tradition to leave the r squared. If you want to square root both sides, you would do 3 over 2 rad cos theta sine theta. I just square rooted everything. I didn't know what to do with the cosine theta and sine theta, you see. All right, you can see that this has some domain restrictions. For example, we would never want theta to be any multiple of pi over 2, because then one of these guys here, either cosine or sine, is going to be 0 and it's in the denominator. That's going to be a problem. But that makes sense anyway, because do you recognize this graph? This is just the graph of y equals 9 over 4 times 1 over x. I just isolated y. Isn't this just 1 over x stretched vertically a bit? So we remember that that thing, if you did 9/4 times 1 over x, that would give you forbidden x and y axes because of the asymptotes involved in the original graph, the way we learned it on our flashcard. So that's just sort of repeating itself once we got here to this final answer. We can see that angles at pi over 2, pi, 3 pi over 2, 0, those are forbidden, and that matches and jives perfectly with our expectations. So the answer to this one is, I'll write it in red, 3 over 2 rad cosine theta sine theta, which has all the right domain restrictions for theta that correspond to the graph of 1 over x vertically stretched a bit. Let's go on to the next one. Okay, so that's part C's answer. X squared plus y squared equals 16. Now you might remember that x squared plus y squared is simply r squared. So the fastest way to do this problem is just to realize that. This is just r squared equals 16. Our goal was to switch to polar coordinates so that our answers had r's and thetas only. But look, we've already done it. The answer is r equals 4. Now you might say, what about that r equals negative 4 solution? Well, if someone told me to draw a circle with radius 4, and they never told me what angle to draw, I would assume that it could be any point in red here along this blue fourth circle. If they told me to graph negative 4, I would have basically replotted these exact same 4 points. Because remember, a negative r just means you face the opposite direction and walk backwards towards a point. For example, this point right here is the point of 4 comma pi over 4. Negative 4 pi over 4 is just this point on the other side, see? But that's the same as 4 5 pi over 4, so it would have been plotted anyway. That's why we often don't use plus or minuses on our polar equations answers. So r equals 4 is good enough. I'm not going to mark you wrong probably if you put r equals plus or minus 4. Notice that sometimes the Cartesian equation, the rectangular equation, is simpler than the polar. I think that happens a bit on number 1, although even the theta equals pi over 4 is pretty simple. Here you can see in number 2, in part B, y equals x squared is so much simpler than sine theta over cos squared theta, right? And here, 4xy equals 9 is so much simpler than 3 over 2 root cosine theta sine theta, see? But when we got to part D, we can see that actually the polar equation is simpler than the Cartesian one. And this happens sometimes. In fact, you could say that this is why we use two systems. In certain types of shapes, like circles, the polar coordinate equations are so much simpler than the rectangular ones. Who wants to think about what x squared plus y squared equals 16 means when they can simply think about what r equals 4 means, a circle of radius 4? Okay, so remember from Algebra 2 days that this really was a graph of a circle with radius 4 centered at the origin, but you wouldn't even need to take any math classes to know pretty much that that's what r equals 4 means, see? So it's just a simpler, more direct meaning. If a circle is centered at the origin, it turns out the polar equation is so very, very simple. Let's look at the next one. It looks like almost the same problem, but this is going to give us a little bit different result. So this time we're going to go ahead and put in the r cos theta. It's going to get squared on its way in. And the r sine theta, that gets squared. And let's pull out the r squared. We have cosine squared theta minus sine squared theta, which should look familiar. That's cosine double angle. So you could write that as cos 2 theta. That's not cos squared theta, that's cos 2 theta. And square rooting both sides, we can get r equals 2 rad 3 over cos 2 theta in a square root like that. Or you could just leave the r squared isolated instead of isolating r. So you could have that, or that. I've basically boxed both answers. The first one is r equals 2 root 3 over cos 2 theta in a square root, and the second one is r squared equals 12 over cos 2 theta. It doesn't matter to me so much which one you use. In fact, if you just want to leave cos squared minus sine squared in the bottom, you could if you wanted, I suppose. Although it's nice to use our identities whenever we can simplify things. The next one we would write, the left side is r sine theta, and the right side as 1/2 r cos theta minus 3. Let's at least get the terms that have r in them to the left side. And let's also clear that fraction. So let's just multiply everything by 2, multiply by 2, multiply by 2, multiply by 2. So we end up basically with 2r sine theta, and I'm going to go ahead and subtract that r cos theta to the left. Let me erase my old work so I don't have too many distractions here. I'll put my previous answer back in here. This was r squared equals 12 over cos squared minus sine squared, or 12 over cos 2 theta, or you can square both sides. Sorry about that little distraction. Back to part F. I just put in r sine and r cosine. I doubled everything. I brought the r terms to one side, and I plan on factoring out that r. So I have r times 2 sine minus cos equals negative 6, and dividing I get r equals negative 6 over 2 sine theta minus cos theta. And that's r isolated. Okay, so let me put my answer there. I'm going to erase some of my scratch work. Put my answer in. R equals negative 6 over 2 sine minus cosine. Box that guy. Erase my old work. All right, the next one's an example. This has a typo in it too. This should have been a 25. Sorry about that. Let's go ahead and plug in the r cos theta and the r sine theta. Make that right side a 25 if you would. So we could get r cos theta minus 5, and this is squared, plus r sine theta, and that is squared, equals 25. And let's be cautious with our FOIL. We get r squared cos squared theta minus 10 r cos theta plus 25 plus r squared sine squared theta equals 25. And you'll see that your 25s cancel. And r squared cos squared plus r squared sine squared becomes r squared what? Times cosine squared plus sine squared. So basically, if I factor out an r squared from the first and fourth terms, I have cos squared plus sine squared. That's Mama's theorem. That's 1, right? There's also still a minus 10r cosine theta on the left, but the right side's 0 now. So what we're saying is this is just r squared minus 10r cosine. Now if you factor out an r, you get r times r minus 10 cosine theta equals 0. So your conclusion is that r is 0. Again, that's the trivial case where you just are plotting up the actual origin. And r is 10 cos theta. So I'm going to write my answer over on the left. Kind of ran out of room there. And I get r equals 0, r equals 10 cosine theta. But if theta is 90 degrees, pi over 2, I would have gotten r equals 0 anyway. So I've got a bit of a redundant solution here. My final answer, I'll just go with r equals 10 cos theta. All right, you'll see later in the book that we actually will come back to this one because it's sort of a special case. All right, so much for converting with equations with rectangular variables into equations with polar variables. Let's look at the converse of that. Hey James, that's Steve Short. Hey, are you still expecting me to come over? Okay, or I'll be there in a few minutes. Okay. Okay, so for this next one, you could change the r to square root of x squared plus y squared, like this, and then just simply square both sides. Once you've reached something like this, you're in a very familiar format. You recognize that this is just the standard form of a circle whose radius is 2, centered at 0, 0. And there's no need to continue solving for y, although you could if you wished. The next one, you could rewrite the theta there as inverse tan of y over x, like this. Don't worry about the plus 180. If you tan both sides, you get y over x equals tangent of pi over 3. But tangent of pi over 3 is rad 3, so you could write this as y over x equals rad 3. In other words, y equals x root 3, which is really just 1.7x. It's y is approximately 1.732x. It's just a line. That's all it is. And that jives with what we believe theta equals pi over 3 is. Theta equals pi over 3 is also just a line, namely this one. And we're saying that there's a representation of this in rectangular coordinates. Y equals rad 3 times x. That makes perfect sense. 1.7x is our slope. 1.7 is our slope. This next one says r equals 10 sine theta. Now, this one would be a little bit hard to solve unless I do a trick. Watch this. I'm going to multiply both sides by r. I'm doing this for two reasons. One, r squareds are easier to work with than r's. And two, r sine theta looks familiar to me. So I'll say that again. R squareds are easier to work with, so I'm multiplying by r. And multiplying by r on the right gives me an r sine theta, which looks familiar to me. So the left side is literally just x squared plus y squared, and the right side is literally just 10y. Okay, now if you want to work on this a little more, you can bring the 10y to the left side and even complete the square. So I'm going to squeeze in a plus 25 there and a plus 25 there, and I get x squared plus y minus 5 squared equals 25. And this is just a circle whose center is at 0, 5 and has radius 5. Okay, the next one, again, I prefer r squareds and I prefer r sines, so I'm going to multiply by r here, here, and here. So triple multiplication there, that's just distributing an r. The left side is x squared plus y squared. The right side is y plus 3r. R is the square root of x squared plus y squared. So I'm really trying hard not to write r. On that last term, I did run into a 3r, and I chose to write it like this. This one's just a little bit hard to isolate y, and honestly, I don't care if you do. Let's move on. The next one, I see an r squared. I'm going to replace that with x squared plus y squared straight up. The right side, I'm not too sure what to do with this. How about write it as x over r? So the bottom is, the left side is x squared plus y squared. The top of the right side is x. The bottom is square root of x squared plus y squared. Now if I multiply this over, I'm taking basically 1 power of x squared plus y squared and multiplying against a half power. So this becomes x squared plus y squared to the 3/2 equals x. And you could easily solve this for y. Just do a 2/3 power. That gets rid of your 3/2 power. Subtract the x squared over. You get x to the 2/3 minus x squared. And even do the square root if you wish. Don't forget the plus and minus. Okay, this next one, I would probably want to cross multiply first. So if I multiply this way and this way, I might get a better look at this problem. Let me switch to blue. I'm going to get 2r minus r cosine theta equals 3. But r is square root of x squared plus y squared. And minus r cosine, see that minus r cosine, that's just minus x. And to solve for y, you would add the x over, divide by 2, square both sides, so you get 3 plus x over 2 squared, and move the x squared over. You could also collapse like terms and stuff like that, but let's just leave it like this. I'll write my final answer like this: y squared equals 3 plus x squared minus x squared. Now why would you want to put a square root on both sides? If you do, you're just going to have a plus or minus. So if you wish to get rid of this square, you're going to have a plus or minus radical here. It's kind of an ugly mess now, see? So it's up to you if you want to do that or not. I'll tell you on the test whether I want you to do that last step or not. But that's how you convert. Notice some of these end up so ugly, they're worse than the thing that we started with. Some of them end up nicer than what we started with. It just depends on the shape. And that's the end of section 8.1. Alright, so that answer, I apologize for the mess here, but that answer is for part F. As you can see, I kind of got carried away there with the work, but this is the answer for part F. So I'll write my answer in here. Y is plus or minus the square root of. And if you want to actually collapse all this, you can. You're going to get a 9/4. You're also going to get basically a 6x. And so forth. So you can kind of just FOIL this all out. But I'll just leave it for now, just for the sake of time, to make sure this video is not too long. You can always kind of collapse this stuff into simpler stuff if you want. Okay, this last one is a little bit advanced, but it uses the same principle. And I think it'd be nice if these were sines, if there were sines and rather than cosecants in the problem. So let me clear the ink and I'll zoom in on this problem. So clearing the ink, zooming in a bit. Let's see here. Going down to this problem. Let's give ourselves plenty of space. So basically, you might want to just multiply top and bottom by sine theta. You don't have to do that at the left side because multiplying by sine theta over sine theta is already multiplying by 1. So this is going to be giving us basically 3 on top and 1 minus sine on the bottom. Okay, so multiplying by sine effectively removed all cosecants and replaced them with 1s. So secant times sine is 1, secant times sine is, cosecant times sine is 1, cosecant times sine is 1, and sine times 1 is sine. Okay, now you can cross multiply. So cross multiplying gives us r minus r sine theta equals, and then 3 times 1. And then if you wish, you could pull out the r. Actually, kind of regret distributing in the first place, you know. Actually, I take it back. Let's back up one step. I'm going to go ahead and change this to square root of x squared plus y squared minus And then that is just y. See the r sign there? So that's just y. And the right side's 3. And maybe we could put the y on the other side again. Just if we wish to clean this up a bit, we might want to write this as 3 plus y. And this is going to be hard to isolate, but you can go ahead and square both sides. That removes the radical from the left and gives you 9 plus 6y plus y squared. Oh, and I can see that my y squareds cancel, so it's not so bad after all. Anyway, this is an interesting problem. If you isolate y, you actually get basically x squared minus 9, then you divide by 6. So you end up with y equals 1/6 x squared minus 3/2. And you'll see that's actually just a parabola. So this equation was that of a parabola the whole time, but it's not always obvious. Who knew that was a parabola, right? It's hard to see that, but it is. So some people actually memorize, if I ever see a secant on top and then a binomial secant statement on the bottom, that's a parabola. You can do that if you wish. But you can always just switch an unfamiliar equation into x and y and see if you recognize it. And that's just a good strategy. So it's not just a type of problem, it's also a technique. If you don't know what graph that is, try converting coordinate systems, and then you say, oh, that's just a parabola. And that's the end of that.